The critical thing in this question is that we're talking about integers that are greater than or equal to at the small end, but less than at the big end. Notice that it's the same thing when they talk about the other interval, greater than or equal to this, but less than that. And so if we look at one of the bars, we would have sort of a dark line here on the left side of that bar, whereas we would have like a dashed line on the high end of the bar. And that signifies that the numbers could be 20, but they can't be 30 because they're less than at the high side. So with this bar, we have numbers that could be 30, but they have to be less than 40. So if they're all integers, the biggest value in that bar is 39. So we can start by just looking at the shapes of the data. They both increase toward the end, but we can see that data set B is starting from 10 to 20 and ending from 40 to 50. A is starting from 20 to 30 and ending from 50 to 60. So we can say that the average, the mean of A is definitely greater than the mean of B. Let's put that on a number line. For the two averages that we have, the average of A is going to be on this side, and the average of B is going to be on this side because the average of A was greater. Now, the question is asking us for the smallest possible difference between the averages. So in other words, we're going to have to push this average as far this way as it'll go, and push this average as far this way as it'll go. Well, how do we do that? The data sets are not exact values. They're kind of giving us ranges here. So we can sort of imagine what is the biggest set of numbers we can put into data set B, and what's the smallest set of numbers we can put into data set A. Just making this prettier here. Okay, so let's start doing that. Data set B, we know that the numbers could be 10 at the small end for this bar, and they could be 19 at the big end. But we're trying to maximize data set B, as we said a moment ago. So for B, we're going to think of the first bar as having, well, it has a frequency of 3. So there's 3 values in that first bar, but we want them as big as possible. So any number between 10 and 19, we want there to be a 19. For the second bar, the numbers that could be 20, but can only go as high as 29, we want them as high as possible. So for those 4 values, because the frequency is 4, we want those 4 numbers to be 29. The next bar, we know that there are 7 numbers there, and we want them as big as possible, between 30 and 39. So we want 7 numbers that are 39. And for the last set, we have 9 numbers. As big as possible is going to be 49. So 9 times 49. And all together, there are said to be 23 numbers. So we don't actually have to add up 3 plus 4 plus 7 plus 9. We know they add up to 23 from the beginning. Let's go ahead and get a number for that on the calculator. 3 times 19 plus 4 times 29 plus 7 times 39 plus 9 times 49, which is 887, divided by 23 is 38.56. Actually, 38.57. So now let's look at data set B. We said we wanted, I'm sorry, that's data set A. We said we wanted data set A as small as possible. So looking at A, for these, let's just write the frequencies. There's 3 of these, 4 of these, 7 of these, and 9 of these. So for the 3 numbers, we want them to be 20. We want them as small as possible within that range. Really, they're from 20 to 29, but we're looking for the smallest. For the 4 numbers, 30. For the 7 numbers, 40. And for the 9 numbers, 50. So we're just imagining, what if we can take the smallest possible numbers for each of those ranges of frequencies that we're given? And they still divide by 23. So let's put that in the calculator. 3 times 20 plus 4 times 30 plus 7 times 40 plus 9 times 50. That's 910 divided by 23, and that's 39.57. So the question is asking us, what's the smallest possible difference between the averages? That means we took the smaller average and maximized it, the larger average and minimized it, and we have 3957 and 3857. The difference between them is exactly 1, and that's why the answer here is B.